I'm thinking of a number between 1 and 1,000,000. You have to guess it, and a bad strategy would take you 1,000,000 guesses. But there's a trick that nails it in 20. Not 20,000, 20. The same trick lets a database find one row among billions almost instantly. It's called binary search, and it's the first real algorithm every engineer learns, and the one interviewers love most. In the next few minutes, you'll see exactly why having beats searching, and why 20 guesses is enough for 1,000,000. This is Logic Lab, where we turn computer science into something you can see. Today, how do you find one thing among millions without checking them all? Start with something familiar, a phone book. 1,000 pages, names in order. You don't read it page by page from the front. That's the slow way, the linear way. You open to the middle. One look tells you, is my name before this or after? Say it's after. You just threw away half the book, 500 pages, in a single glance. You never look at them again. Now you open to the middle of what's left and ask the same question, before or after, and again you toss half. That's the whole idea. The data must be sorted, that's the one rule. Because it's sorted, every comparison doesn't eliminate one option. It eliminates half of everything that remains. Let's make it exact with a sorted row of numbers. We track two markers, low at the far left, high at the far right. The answer is somewhere between them. We look at the middle element, halfway between low and high. 3 cases. If the middle equals our target, we're done. If the middle is too small, the target must be to the right, so we move low to just past the middle. If the middle is too big, the target is to the left, so we move high to just before it. Then we repeat. New middle, compare, discard a half. Watch the gap between low and high collapse, 16, 8, 4, 2, 1. Each step the window of possibilities is cut in half, until only the answer is left standing. Now the magic number. How many times can you have 1,000,000 before you reach 1? 1,500,000, 250,000. Keep going. It takes about 20 halvings. That count how many times you can have n down to 1 is the logarithm of n. So binary search runs in O of log n, and log n is astonishingly flat. 1,000 items, 10 steps. 1,000,000, 20. 1,000,000,000, 30. Multiply the data by 1,000 and you add just 10 steps. That's the curve every engineer dreams about. Compare that to the linear search, checking one by one, which is O of n for 1,000,000,000 items. That's 1,000,000,000 steps versus 30. Same answer. The difference between a system that scales and one that melts is exactly this. But binary search is famously easy to get wrong. Interviewers know it, and they watch for the traps. The classic bug, the loop boundary. Is it while low is less than high, or less than or equal to high? Off by 1, and you either miss the last element or loop forever. The other trap is computing the middle as low plus high divided by 2. On huge inputs, low plus high can overflow. The safe form. Low plus the quantity high minus low divided by 2. Same midpoint, no overflow. Small detail, the kind that separates code that works on the whiteboard from code that works in production. Here's the part that makes it worth mastering. Binary search is everywhere, often in disguise. Your database's index. Binary search over a sorted structure. Looking up a word in a dictionary app, Git bisect hunting the commit that broke your build, even guessing game solvers, all the same having idea. The deeper lesson. The power didn't come from a faster computer. It came from keeping the data sorted, which let one comparison carry the weight of 500,000. Structure beats brute force. That trade, do some work up front to sort, search almost for free forever after, is the soul of good algorithm design. Recap. Sorted data plus the halving trick equals binary search. 2 markers close in on the answer, throwing away half the search space each step. That's O of log n, 20 steps for 1,000,000, 30 for 1,000,000,000. Mind the boundary and the overflow, and you've got the workhorse behind every fast lookup. Halving was so powerful we got the answer almost for free, but it needed sorted data. So next we ask the obvious question. How do you sort a pile of things in the first place, and which method wins? That's 2 ways to sort next on Logic Lab. See you there.